Section 9.3 is solving quadratic equations. I can solve quadratic equations by graphing and using square roots. Big ideas here. Quadratic equations can be solved by a variety of methods, including graphing and finding the square roots. In many cases, the negative solution of a quadratic equation will not be a reasonable solution to the original problem. If you look at the note on page 561, it talks about the standard form of a quadratic function, which we've talked about before. In standard form, we have to have our highest exponent. So here in quadratics, it'll be x squared first. So we'll have ax squared plus bx plus c. The solutions of a quadratic equation are the x-intercepts of the related function and are called the roots of the equation or zeros of the function. In example 1 here, we're going to solve by graphing. So the solutions of each equation are what we're looking for. And remember, when we're looking for solutions, we're looking for what do our variables equal. We're going to use the graph of the related function. So here my first step is going to be to switch this back to the related function. So I'm going to make it so that y is 0. I'm going to put a y in for 0. We can only do that substitution when it's 0, guys. And that's going to give us our x-axis, and that's why it works. Because y equals x squared minus 1 is just going to be our x-axis, and that's going to tell us what our x's are when y is 0. So our first step here is to use a table of values. Again, we check to see if we have a b value. Here we don't. No linear term there. So our b is 0. We don't have to worry about it, so we can center at 0 with -2, -1, 0, 1, and 2. Now, we take our x values and substitute them in to our function. -2 squared minus 1, 4 minus 1 is 3. -1 squared minus 1, 0. 0 squared minus 1. 1 squared minus 1. And 2 squared minus 1. Now we can graph our coordinates here. And I'm going to be at -2, 3, at -1, 0, at 0, -1, at 1, 0, and at 2, 3. And we connect those dots here. Now, our solutions are when y is 0. They happen at our x-intercepts here. So I have two solutions. I have two places where I cross the x-axis. X equals -1 and x equals 1. So here I have two solutions. In B, I'm going to start off the same way. With my table of values, I substitute them in. And this is our parent function, guys. Again, remember, we write our related function, so we put our y in there, and it's our parent function. So 1, 0, 1, and 4. Again, 2 squared, 4. 1 squared, 1. 0 squared, 0. So I'm going to be at -2, 4, at -1, 1, at 0, 0, at 1, 1, and at 2, 4. And I can get those, guys, if we don't recognize that x squared equals y, or x squared equals 0, the corresponding relation, the related function is x squared equals y. If we don't recognize that's our parent function, we can go ahead and do our table of values and substitute them in and find them that way. If you recognize that it's a table of values, though, we can go right to -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Over 1, up 1 in both directions, over 2, up 4 in both directions. And again, here we're still looking for our solutions. So we want to know, what does x equal? Okay, and we want y to be 0. Here that happens at 0. So x equals 0 is my solution. And I just have one of them. I only touch or cross the x-axis in one spot, so I have one solution. Now for C here, it's going to be x squared plus 1. So my related function, I set y equal. And what I'm going to do, guys, is since I already did x squared here, I'm just going to go ahead and add 1 to these just to save us a little bit of time. So I'll get 5, 2, 1, 2, and 5. And I'm going to graph these in yellow. Negative 2, 5. Negative 1, 2, 0, 1, 1, 2, and 2, 5. Keep in mind here, guys, we are looking for our solution, which is our x-intercept or our 0 of our related function. Here, we don't have any. We don't have anywhere where it crosses our x-axis. We have no solutions here. So our options with quadratics, guys, we can either have 2 solutions like we did in A, 1 solution like in B, or no solutions like in C. Now, what's the solution of each equation? Use a graph of the related function. I start off with an xy table here, and my initial values, negative 2, negative 1, 0, 1, and 2. And that's because, again, I don't have any linear term, no bx, so my b is 0, and so we start at 0. I substitute those in. I get negative 12, negative 15, negative 16, negative 15, and negative 12. Now to graph here, I'm going to go to negative 2, negative 12. I'm going to have to change my scale here. I'm going to go by 2s. So I'm going to go negative 2, negative 4. And when we change our scale here, we do not have to change both scales to match. So I can change my y-axis without having to change my x-axis. Now to graph our points here, I'm going to go to negative 2, negative 12, negative 1, negative 15, 0, negative 16, 1, negative 15, 2, negative 12. And if we look here, guys, we can tell that our branches are going to come up somewhere and cross through our axis. But the way that I drew my branches here, guys, I crossed at 2 different spots. It's not very precise. So I need some more points. I need to know a better picture of where this graph is going to go. So in order to do that, I need to find some more x values. So let's try 3. 3 squared minus 16, negative 7. Okay, gives me a little bit better of a picture, but it's still a little bit of guesswork. Is it going to be at 3.5? Is it going to be more towards 5? Is it going to be 4? We're not really sure yet, but what we do know is that it's symmetric. So if I'm at negative 7 for positive 3, I'm also at negative 7 for negative 3. We could also put negative 3 in, but we don't need to there. It's symmetric. We can try 4. 4 squared minus 16 is 0, and we finally got to our axis here, what we're looking for. And now we can draw in our parabola. And it's still not perfect by any means, but it at least gives us a little bit better of a picture of where we're going. Our solutions then, we have 2. X equals 4 and x equals negative 4. And we knew we were going to have 2 solutions because of the way that our branches were going to go up. We just didn't know where they'd be. And that's one of the reasons, guys, that we have a lot of methods that we use to solve quadratics, is because sometimes graphing just isn't feasible. Our points are too far away, or what if it falls in between 3 and 4, for example, and we have to guesstimate. We don't want to have to guesstimate. We want to know for sure where our solutions are. In B here, same thing. We're going to use the table of values. We substitute in our x's. $18, 9, 6, 9, and 18. At negative 2, I'm at 18. Negative 1, I'm at 9. 0, 6, 1, 9, and 2, 18. So the difference between this graph and our first graph, guys, is even though this one never crosses our axis either, we don't have to use more points because we know that our vertex is either our maximum or our minimum. Here it's our minimum point, which means we know we're never going to go below that. We're never going to cross the x-axis. No solution. Last one here for C. Before we can set it equal to our function here by setting it equal to y, it has to be equal to 0. So I need to move this minus 25 to the other side, and to move it to the other side, we do the opposite and add it. And here they both happen to cancel out, so I get x squared equals 0, which again is our parent function. So at negative 2, 4, here remember our scale, negative 1, 1, 0, 0, 1, 1, and 2, 4. And again, we only cross in one spot, so here my solution is just x equals 0. One solution there. And again, I didn't write it every time, but the reason this works is because we're graphing the related function. So it's like we're replacing that 0 with a y, which gives us our x-axis. Replacing the 0 with a y. Once we get it set equal to 0, we're replacing that 0 with a y. One other thing here, guys, these don't both always cancel no matter what. It just happened to be here that negative 25 plus 25 is 0. And so they both canceled. If this would have been like a minus 36, for example, then we'd have had an x squared minus 9 and would have gone from there. So be aware of that, guys, that it might not always just cancel. And I'm going to stop this video here and I'll continue on in another video.